Welcome to Lecture 8 of our IAP series on building sound. My name is Phoebe. I'm going to be talking today about TTS. So this is our first lecture bridging from just music audio synthesis into speech synthesis, which is part of the bread and butter of what Gridspace does. So just to kind of look at the schedule overall, we've been through all types of synthesis, and essentially we've been building cool audio that sounds good. And that's kind of been the theme of the first half of this month. And so now for the second half of the month, we are now looking at building speech that says the right thing and sounds really good. And I'm emphasizing that because humans have a natural tendency towards being very discriminative with regards to how natural speech sounds. We're very prone to noticing when things fall into the uncanny valley. So any kind of synthesis of speech has to be really accurate in order to not fall into that robotic sound. And just to kind of say this another way, we're taking text and we're turning it into a high-dimensional waveform that still contains the text. So this is not just making audio that sounds good or audio that sounds natural. It's got to say the right thing. There is a correct here. And then we're going to do it in real time eventually. So this is, just to go back to what the actual schedule looks like. We're going to start with parametric and concatenative TTS, which are kind of older methods. Looking at some of the history, we've got some guest lecturers, which I'll kind of explain later. Then we're going to start on kind of early neural TTS, and then move into modern neural text-to-speech. So that is the landscape for the next few weeks. So just to say it again, in speech synthesis, there is a correct. I can say things that sound very natural, and sounds like perfectly natural speech, but no information is being carried there, so we can't really call that. There's no linguistic or informational content there. So there is a correct, there is a natural. I'm not very good at doing a robot voice, but I'll demo some, and you can carry all the information without it sounding natural. It can sound completely robotic. So there's these kind of two axes that we're going to be kind of optimizing for. So these are just kind of some of the aspects of that make it hard. Like, not to drive home this point too hard, but speech is quite a lot harder than just music. Not just music, but you know what I mean. So it's an information carrier. There's a lot of articulation that needs to happen. There's intelligibility, there's sequential dependence. So the way our phonemes change over time and the way one phoneme fits into a word might be different dependent on the phonemes before it and the phonemes after it. We're going from a low-dimensional text, just words, like a one-dimensional signal essentially, into this kind of high-dimensional waveform. And we've got to trust that it contains the same information, or make sure it does. And then as far as naturalness goes, there's frequency content and perception, word boundaries and psychoacoustics. So word boundaries that we kind of see on paper with white space, we mostly, when we're listening, we hallucinate them. They're not actually, there's not necessarily, if you look at a spectrogram, a concrete gap between words. There's usually more of a gap right before a fricative as you close your mouth. But a lot of words just blend into each other as far as the audio goes. So that creates another difficulty. So text-to-speech. So just going over our types of music synthesis, these can actually all of these have a direct correlation to how we build sound for speech synthesis. And so we can kind of see additive, subtractive, formant wavetable, and physical modeling in parametric TTS, which we'll talk about later. And then just starting with the most intuitive one, granular and sampling, where we're taking small chunks and we're just adding them in sequence in the time domain, is kind of akin to concatenative TTS. And then we also have neural synthesis later. So these are kind of our broad areas of speech synthesis. We have concatenative, then we have all of these parametric ones, formant, articulatory, statistical. We have physical modeling, and then neural synthesis. And these are the ones we're looking at mostly today, although I will cover a little bit of the other ones in kind of the history section, except for neural synthesis. That is, we have all of the lectures of next week dedicated to neural synthesis because it is the best way of creating speech synthesis that we have right now. So, okay, let's start a little bit with the instrument, with our vocal tract. So earlier in the series, I was posed the question, is a human vocal tract an open or a closed pipe? And so I have an answer. It is actually a closed pipe, where the bottom of your vocal fold is actually the closed end and your mouth is modeled as the open end. I did a bunch of looking to try and work out if when your mouth is open, it's open, and when your mouth is closed, it's closed. And I couldn't really find a good answer. Everything was telling me that it was a closed pipe. That didn't make sense to me. So I just tried going, I can actually just play it rather than demo it because that's easier. So in theory, right, if I close my mouth and it turns into a closed pipe, we should see a change in the fundamental frequency because it becomes half rather than a quarter of the length of the wavelength. But the fundamental didn't actually change. We can kind of see this in more of the formants here. They're both at this kind of 200 hertz. So I think regardless of whether your mouth is open or not, maybe it's because of your nasal tract. The vocal tract is a closed at one end, open at the other end pipe. But we do see this change in the ratios of the harmonics that make up something like a consonant, like a and more of an open sound like an R. And we'll get into modeling these later, but this is a large fact. This is the main way in which parametric TTS operates, is modeling these formants. So essentially, we have our source, right? We have an oscillator in our throat, our vocal folds, that's creating a constant pitch. That's where the fundamental frequency comes from. And kind of similar to when Nico was talking about subtractive synthesis, this is just generating a waveform. And then everything else, all of your vocal apparatus here, is what's kind of molding that, creating filters on top of that generates the exact sound that comes out your mouth in the end. And then we have articulatory consonants made by the building up of air and plosives with the lips and the tongue. And like I say, all of the different ways that we operate this creates these different formants, and that's how you get all these different phonemes. And kind of the more you think about it, the more complicated it feels, right? How do you model something that I'm not thinking as I'm speaking, right? How I'm exactly moving my mouth to make these different frequencies. I'm just speaking. So phonemes. We talked kind of a bit about them. It's just kind of the phonetic spelling of words, or the phonetic atoms of speech. So where these phonemes sit depends, like h sounds are in your throat. As I said, plosives are very far forward, so that's the P's and the B's up here. And yeah. Other complications with creating speech, I said before, like phoneme boundaries, word boundaries. So we have more complex vowels. You can't just list out all of your phonemes and have them one after the other. The phoneme before might change the sound of the phoneme after. So like the word tire, which I guess I will find the slide for later. But it's 3 vowels essentially, tire. And it's not like like they blend together. You kind of get the idea. So that's diphthongs, triphthongs. So that brings me into the first type of TTS, which is concatenative. And this is kind of in the name. You concatenate different atoms of audio together to create the word. And just to demo a kind of really dumb one that I've got hooked up to my keyboard here, I've just kind of hooked keys up to me saying different letters. And I'm going to try and use it to create this. think I got there. Peter Piper picked a peck of pickled peppers. And then just to kind of play it all together. Yeah, sure. So some of the, like, I don't know, from the crowd, what are some of the cons of this approach?
Sounds bad.
Thanks, it sounds bad. More specifically, it sounds disjointed. That's one, like getting sounds together. Anything else?
It doesn't identify how they interact with each other.
Yep, there's no like way in which one of the letters changes the other. They're all independent audios.
You can't understand it.
It's completely unintelligible. Thanks. Yeah. Other ones is just that it's
Too many repetitions.
yeah. So
And, sorry.
no, go for it.
One interesting thing is that P doesn't make the puff sound, it just makes the P part of the sound.
Yeah. So just to reiterate those, one of them was that too many repetitions. So this has a lot of P's in it, and we very quickly hear it being unnatural because it's just getting, even if it was correctly joined up, the same sound over and over again. Humans are very good at noticing when things are just like direct repeats. And the other thing is that the P sound, Peter Piper picked, they're different P's depending on where they are in the word, and we're using the same P for each of them. So concatenative TTS, actually the memory limits of it blow up pretty quickly. If you had to store every single way in which someone creates different variations of the same phoneme, and then you'd have to pick them correctly in order, and then join them up incorrectly with some kind of blending to make it sound good. Like, this is a very bad version. There are much better versions, and we'll kind of show some of those later. Can anyone tell me a pro of this approach? Good thing. It's easy. It's very, like, yeah, it's easy. It's intuitive.
There's a much smaller number of building blocks that you got to work with. Like, instead of having to think about the entire English language, you've got like there's still a lot of them, but much fewer phonemes.
Yep, there's a limited set of things that you can use, so it's much simpler. And also, if your goal is just informational, right? You can set this up in a way that you can get your information across. If speech is just a carrier for information, then this is it functions, it works. A final pro is how much control you have. There's no chance of the text that you are outputting not mirroring exactly what you're trying to make, because you're just looking up audios and putting them together. There's no risk that you're not going to end up with the same information in the text input as in the audio output. So just to kind of go over one of the things of it being disjoint, this is an example of Taya, a triphthong. Just me speaking it normally, and then me speaking each phoneme and adding them together. And we can kind of see in the spectrogram for normal how fluidly the phonemes fit together, and how difficult that would be to emulate with any kind of concatenative TTS. And people have tried, and there's some reasonably good approximations to it just with smoothing, but it's not the same. So yeah, limitations: sequential dependence. Artificial phoneme boundaries. It tends to come across as very robotic because the pacing as well. There's no sense of fluid pacing when phonemes have a specified duration. And then low control over the prosody of the voice. You don't have natural overarching intonations, unless, of course, you program it to do that, and then it becomes very programmatically complicated very quickly. So that's the end of, I'm going to take a brief segue into early TTS. Any questions on concatenative TTS? It's pretty straightforward. Nice. So the history of TTS starts back in like 1700s, when people started using like mechanical TTS, so resonators to create vowels. And Kratzenstein had this vowel organ in 1780. And this was just different shit. He just had different physical resonators to try and create different sounds of the vowels. And mechanical synthesis kind of kept going all the way through to the kind of 1800s. Famous one, Wolfgang von Kempelen. He modeled, I'm going to play this and then I'll explain it actually. So who thinks this is a good informational carrier? Great.
Saying help me.
So he modeled the lungs as this set of bellows and the vocal tract as a leather pipe. He had this kind of compressed air reed system for kind of lips and things and tried to get intelligible things out of that with limited success, but it was the first kind of physical, mechanical approximation of a human speech kind of mechanism. Another guy at the time actually also got his dog and just got the dog to bark while he physically manipulated the dog's vocal tract and managed to get the dog to speak. I would say no animals were harmed in this, but I really don't know. It was the 1800s.
I love this. Looks like it's from a patent.
It might well be, honestly. I just love the fact that they've labeled the nostrils. Speech sounds come out here. Essentially, yeah. So then in the 1900s, we moved to electrical synthesis. And this was when things kind of got better, honestly. Mechanical synthesis, now there's a bunch of physical modeling techniques, but it's still kind of simulations. There's no real modern day example of a mechanical physical system. So a famous example in 1939, there was the voda, which is kind of a shortening of vocoder. And this was the first that used a kind of analog source, so some kind of analog oscillation source, and then applied analog filters to it to create different formants, different audios. And this sounded like this.
Say she saw me with no... Now say it in answer to these questions with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
So this is pretty damn cool. Like, they've got the intonation as well. That's what he was kind of showing with the question answering. He had the prosody there. So that was something that was missing a lot from the concatenative TTS. But this was extremely difficult to operate. Like, whatever magic this guy's doing with his keys to like vary the kind of the filters, the source to get that prosody, definitely not a layman's device.
Say she saw...
So then in 1961, we had our first digital TTS synth. So this was IBM. And this was, if you were here for the very beginning, we played Daisy. So they got this machine to sing. And that was kind of a famous audio clip. It's been reproduced on 2001 Space Odyssey. This worked as a series. It was essentially kind of concatenative TTS, but where each of the things was a function generator for each of the sounds rather than storage. And it kind of did frequency modulation. So kind of call back again to the music synthesis. It frequency modulated these kind of phoneme functions and to generate the speech.
Daisy, Daisy, give me your answer to. I'm afraid.
And so that's how they also got the different pitches, so they managed to get it to sing. This thing weighed like 100 pounds. This was a monster. So then, fast forward to the 1980s, and we have deck talk. And this is an extremely famous one because this is the original TTS for Stephen Hawking. This also relied on like source filter models. So it had source and informant. This was a parametric TTS, and it sounded like this.
The fact that you are listening to me now shows what technology can do, even if it does give me a Scandinavian or American accent.
So a theme with all of these is that they still sound pretty robotic. Daisy, Stephen Hawking, like it still falls into the uncanny valley. We can very easily discriminate that this is not human. So that brings me to parametric TTS, which is the robotic one. I'm not actually going to get out of that until we get to neural synthesis, really. But just kind of diving into how parametric TTS works. Does anyone have any questions first about like history of TTS? Cool. So this, as I've kind of said multiple times, relies on this source filter model. The source tends to be just kind of an impulse generator, but with this kind of voiced flag. So again, phoneme-wise, if you want to touch your vocal folds and kind of go, and then you'll notice one vibrate. Most phonemes come in pairs. There's a voiced version and an unvoiced version. And so the formant that the shape of your mouth is the same. The difference is whether you are like kind of singing into your formants. So that's kind of here with this voiced and unvoiced. The input to the filter could be white noise or like something with an actual pitch. There's a gain, and then we have some kind of filter, and you get out speech. So that's source filter modeling. So the main kind of challenge with parametric modeling is how you get the acoustic features that you're going to use to turn your source into like speech. A lot of the acoustic features that we could use are things like your pitch, your fundamental, your envelope, kind of high pass, low pass filters. These are just kind of pulling from the air. I was going to ask people to actually kind of give me some, but I forgot, and now I'm on this slide. So they're here. But moving on to like how we actually get these. So again, this is kind of the source, the oscillator. So this is Peter Piper picked a peck, and you can see here how much the pitch varies over time. From 0 for the like unvoiced segments to something high. So we can have, so let's say that's one input to our source filter model for speaking a sentence. We're trying to speak a sentence. And one input is this time varying pitch signal. Great. We already talked about this formant kind of synthesis. So the way people tend to get formants or like model them is with LPC, so linear prediction coefficients. These are used because they're kind of more tractable than a lot of other kind of filtering methods. It's essentially just an IIR filter that you kind of put on top of the oscillation. Let's move to this for a second. So it's an all-pole resonance modeling. So poles means just that there's no zeros in your filter, like transfer function. So if we're modeling this as XZ being our like speech out, EZ is our like source in, and HC is the transfer function that we're putting on top of it. And then we can model that as this all-pole resonance modeling because it's more tractable, it's entirely autoregressive actually, and it's it's simpler to model than an FIR filter or a mixed and armor filter. So rearranging this, we get, and then kind of like converting it back into the time domain, we kind of see that it's this set of coefficients acting on time delays of previous samples. And this is the part that makes it autoregressive, and these are the filter coefficients that we're trying to find. The other thing that makes this tractable to kind of find is that you can actually get these coefficients just by autocorrelation. So if you scan autocorrelation functions across your signal, there's a very easy way to find these filter coefficients for a formant, for a given sound. So once you've got your LPC filter coefficients, the number of, you then, the other kind of design you have is how many poles you're going to have. So how many coefficients you're going to have. And this kind of, we can see different values give you different amounts of, what's it called? Granularity, I guess. And this kind of can determine how much, got a good word, resolution, I guess, yeah. How much resolution your spectrogram or your audio signal has. We can see this with the 40 pulse order. And again, this is the original and this is the 40 pulse order. So that robotic voice is obvious even from this. With formant filtering, with LPC filtering, you get a good approximation to the sound. You can generate something that's intelligible. But you lose a lot of the kind of aperiodics in there that create kind of the naturalness of sound, of speech. So yeah, and this is just kind of that formant filter on top of a DFT, so you can kind of see the correlation there. So once you've got your, let's say you're looking to reproduce a sound that's like, and you've found your formant filters, the next question is, let's say you're generating a sentence, right? You've got coefficients for every single phoneme. How do you actually, surely this is just as bad as concatenative, right? You're still just like modeling each individual phoneme. Well, the joy of filters is interpolation, and you can much more easily kind of blend between things if you've got a constant source and you're just varying a filter on top of it. There's no direct kind of cutoffs. And that brings me to our speak and spell. So if you stay tuned on Friday, we've actually got one of the inventors of the speak and spell. So this was a huge leap forward in TTS. Like before this, it was entirely kind of that massive machine, and then like Stephen Hawking's deck talk that we saw in the history.
Spell level A. Press go to begin.
That's all LPC parametric filtering. So that is not concatenative. That's not just kind of choosing audios and putting them together. This is actually the original chip. And you can see here it says parameters storage kind of zone. So it's essentially got a stored lookup table of LPC parameters. It's got some, where is it? Somewhere in here, it's got an oscillator, some kind of impulse, digital impulse oscillator, essentially. And then we've got this lattice, which is the kind of the thing that's piping that different oscillators through those LPC parameters. I think it's got 8 different channels that it layers on top of each other. This was kind of revolutionary. Like, look how small it is. And it's generating it on the fly. It's way better than my little samples. So this is, again, each of these lattice pieces. We can see this kind of 1 period delay. The excitation comes in, and like the delay is, like I was showing, these parameters create an autoaggressive filter. So any questions on that?
So do you type in a word to the speak and spell and then it says it, or what is it? What do you
No.
do?
It's for kids to learn how to spell. So it gives you a word. So if I do press go on this, where is go?
Spell answer.
And then I have to.
A N S W.
I'm really concerned I'm going to get it wrong now.
Now spell one as in one word.
It's for kids to learn how to spell, which by itself is pretty awesome. That one of the revolutions in like speech synthesis was for something as, no offense, but arbitrary as a learning to spell toy for kids. Like the fact that this contains like very, very new technology is really quite funny to me. And we've got, like I say, the inventor of this giving a lecture tomorrow, giving half the lecture tomorrow. So tune in for his take on the speak and spell. So just to kind of, this is still very highly controlled. We've still very much just entirely, we're doing a lookup table. It's kind of got the same control pros as concatenative TTS in that it's impossible for it to say the wrong thing. We're just kind of doing lookups and then interpolating them together. So it's a lot smoother, the sound quality is a lot better, but it's still very robotic. And there's still very much a lot of human input into designing those, into choosing the samples that go into this. And so kind of moving away from that towards kind of segueing into the modeling part of TTS. What if there wasn't? What if what if these coefficients were generated by a statistical model? So this was kind of the next stage for LPC source filter modeling, was rather than having a lookup table for LPC coefficients, they used statistical acoustic modeling, so HMMs for generating those acoustic features. HMMs are good for acoustic modeling because of their, like, it's sequential statistic kind of transitions, right? Like, given that I've said this phoneme, what's the chance that I'm moving to another? And you can kind of train an HMM to generate those waveform features. And then once you've got those waveform features out, you put them through kind of the vocoder, which is the source. The source filter model is a type of vocoder, and I think Lokman's going to be talking next week on more complex vocoders, but sticking with that one for now. Cool. So actually, now that we've moved into HMMs, we actually move away from LPC coefficients. So statistical modeling tends to use MFC or MGC, so mel frequency cepstrum coefficients. Sometimes it uses like Bach frequency cepstrum coefficients. These are all different ways of modeling kind of the pitch output of speech, but we're no longer modeling just like a filter, right? We're now modeling, it's all kind of similar in that these are all different ways to explain the power amount of different frequencies in a speech signal, which is kind of what you need to reconstruct that speech. It's just those ratios of different frequency bands. But these are just different ways of kind of encoding that. So this is kind of a diagram of how an HMM-based statistical parametric speech model kind of looks like. So they're using subband basis vectors. They're using, again, always that log F0, that frequency fundamental. See? It's a good question. HMM is hidden Markov model. So it's a way of modeling state transitions based on probabilities. This actually technically isn't a vanilla HMM. It's a HSMM, hidden, I think that's not hidden semi-Markov model, because it's based in statistics. I can't remember why it's a semi, but it's only a semi-Markov model. Someone can Google that. Cool. So that brings us to the end of parametric and these three methods of doing kind of parametric modeling. First of all, with lookup and interpolation, on-the-fly analysis, and then kind of statistical modeling to pull out those parameters, put it through a vocoder, get it back. Any questions on that? I kind of breezed through that part pretty quickly. Cool. So these also have, like I say, kind of limitations as far as being robotic goes. We saw that with the smooth response in the spectrogram when we put it back through the vocoder. They're pretty complex human-centric descriptions of speech. Like, this is all humans being like, if we wanted to recreate this exact sound, what information do we need to do so? And like fundamental frequency, band aperiodicity, which I didn't really talk about, but that's kind of those natural frequencies that aren't just like they're not the periodic frequencies. They're not the fundamental, they're not the kind of main formants, they're the bits in between. And yeah, it's kind of humans looking at speech and being like, okay, if I wanted to reconstruct this, what information would I need to know? How do I model that? That has the limitation of human imagination to a degree, and also just computation, which is something that neural networks are great at, which we'll get to. And then HMMs themselves have kind of limited modeling capabilities. There's no history per se, like memory is pretty limited with HMMs, and they're not, yeah, they have their limitations. Cool. So I kind of wanted to do a bit of a preview as well of just like, this is kind of moving more into DNN. This is an HMM, hidden Markov model with a deep neural network together to create this, to kind of generate these features, but it's kind of the same idea of generating features and then putting them through a vocoder. And so this is Synth. So this is kind of our preview into neural networks for next week, but this is singing synthesis. So again, you can still hear the slight, like it still falls in the uncanny valley to my mind. You can still kind of hear the edges of the phonemes to a degree. It's not generating the whole thing as one, but we got to that from so yeah. Oops. So I'm finishing a little early on this, but that's kind of all I've got for today. So next lecture, which is tomorrow, we'll be talking to Gene Franz, the inventor of the speak and spell, and Sandy Disner, who is a linguistics researcher at USC, who has worked on speech synthesis from the linguistic side of things. So we'll be getting their two takes on speech synthesis and what they've worked on. And then next week, we're going into early neural TTS, so seek models, WaveNet, and then moving into kind of deep modeling from there. Any questions or concerns?
Since you just are, this is fresh in your mind now of like early TTS, is there anything from this that like deserves to make a comeback now that we have like really great hardware and like we know a lot about deep nets and stuff? Like, do you think any of this stuff could help still?
So the question was like, with this fresh in mind, do I think any of this kind of from early TTS should be brought back into the modern day realm of TTS? I think it would be kind of interesting to do more acoustic feature input to TTS. Like at the minute, we're still going from a very low dimensional, non-descriptive signal a lot of the times without many other kind of descriptive acoustic features. Now kind of TTS, modern neural TTS is moving towards having like pitch inputs, articulation inputs, or just like different speaker inputs, but kind of getting like having acoustic features as input to a model is kind of, I see no reason why that wouldn't be extremely helpful. And now that kind of modern neural methods can make better use of that, I think that would be cool. I actually think physical modeling should make a comeback. Honestly, like mechanical modeling of TTS, like this is kind of, I don't think it's going to be as good as neural networks, but we kind of dropped at that in the 1800s and kind of went, well, this kind of sucks. I think it would be kind of really fun to make some kind of physics-based model of like the vocal tract and see what we can get out of that. I think it would be extremely difficult and probably not very good, but why not? So cool. Thanks everyone, and join us next week. Tomorrow.